For years, quantum computing has always felt like the technology of tomorrow. Well, guess what? Tomorrow is here. 2025 is the year the hype finally starts to fade because the real world results are starting to speak for themselves. This is the beginning of what we're calling the quiet revolution.
And that right there, that quote, it's really the heart of this whole thing. I mean, this stuff is officially out of the lab. We're talking about it being deployed in high-stakes industries like finance and manufacturing, tackling problems that, honestly, we used to think were fundamentally unsolvable.
And you know what follows real-world use cases, right? Money. The quantum computing market is on track to blow past $1 billion by the end of 2025. This is way beyond a university project now. It's a seriously powerful new economic engine.
Okay, so what does all this power actually look like in the real world? To really get it, we need to move away from the abstract and zoom in on a concrete problem, a manufacturing puzzle that perfectly shows what happens when you bring this new kind of computing to the table.
Okay, this is where the rubber meets the road. Just look at these numbers. Ford Otosan had this ridiculously complex scheduling problem with their welding robots. Their old-school classical system would literally grind away for 10 hours to come up with a workable schedule. The quantum hybrid approach, it found a better solution in under 5 minutes. But here's the crazy part. It wasn't just about speed. Look at the constraints. It was juggling 16,000 variables compared to the old system's 1,000. That's not just a little improvement. That is a complete game changer. So how on earth is that even possible? Well, it all comes down to a totally different way of thinking. A classical computer is like someone trying to find the highest point in a mountain range by just walking. It follows one path at a time, and if it finds a pretty high peak, it might just stop there, thinking it's the highest one. That's what we call a local optimum. A quantum computer, because of this amazing principle called superposition, is more like a cloud that covers the entire mountain range all at once. It sees every peak, every valley, simultaneously. It doesn't get stuck on a good enough hill, it finds the actual highest peak, the true global optimum, in a flash. Now, a result like the one we saw with Ford doesn't just pop out of a single magic chip. Nope. It's possible because the entire technology stack, the whole ecosystem, has finally come of age and is working together in perfect harmony.
So in 2025, the whole setup really boils down to 3 key layers working together. First up, the hardware. And it's not just about cramming in more qubits anymore. The real focus has shifted to making better qubits, ones with higher quality and better connections. Second, the software has gotten way smarter. It's more dynamic, and it's constantly talking to the hardware. And number 3, and this is probably the most important thing to get your head around, is that this is a hybrid world. We now have the QPU, the quantum processing unit, acting like a super powerful coprocessor, sitting right alongside our existing CPUs and GPUs and jumping in to tackle only the gnarliest parts of a problem.
Okay, but we've got to pump the brakes for a second and inject a serious dose of reality. This isn't about some quantum supremacy fantasy where these new machines replace everything we have. Nope, it's about something much more practical: quantum utility. It's about finding those specific, high-value problems where this new tool gives us a genuine, undeniable advantage. So, the obvious question is, right, is quantum the magic bullet for every hard problem? And the answer is a big, fat, definitive no. Let's not forget, classical computers have been around for decades. They are incredibly powerful, highly optimized, and for most jobs, they are still absolutely the best tool for the job. So you'll hear this term thrown around a lot: NP hard problems. Basically, these are the kinds of problems that get exponentially tougher the bigger they get. But here's the kicker. It turns out that our classical computers have gotten ridiculously good at finding clever shortcuts and good enough answers for a lot of them. So the bar for quantum to actually be useful is incredibly high. So where does quantum actually have an edge today? Well, it really shines when problems have extra layers of messiness. Think about it. You're trying to build a financial portfolio where you want to maximize your returns, but at the exact same time, minimize your risk. Those two goals are fighting each other. Or trying to predict the needs of an energy grid when you don't know how windy it's going to be tomorrow. These are the random, uncertain, multi-layered problems where classical methods start to sputter, and quantum's unique view of the world provides a real, tangible advantage. All right, so that's where we are right now. But what about the road ahead? What does the rest of the decade look like? Well, the foundation that's being laid today is really setting the stage for a massive technological and economic transformation down the line. I mean, just look at these projections. The numbers are absolutely staggering. By 2035, we're talking a potential market value of upwards of $72 billion in finance alone. This isn't just a new gadget, it's a foundational economic shift for entire industries. And there's a pretty clear roadmap for how we get there. Right now, we're in the quantum utility phase. That's about solving real problems today. Next up, by around 2027, the focus shifts to scale and reliability, just making bigger and better systems. But the real holy grail, the big leap everyone is aiming for, is fault tolerance, around 2029. That's the point where these machines get stable enough to run incredibly complex calculations without errors, unlocking things we can only dream of today, like perfectly simulating new molecules. Now, it's not all smooth sailing, of course. There are a couple of huge hurdles on the horizon. First, there's the ticking time bomb known as Q-Day. That's the theoretical day a quantum computer becomes powerful enough to shatter most of the encryption that protects, well, everything online. And second, we have a massive people problem. There is a serious global shortage of talent. We just don't have enough people who know how to build and program these things. So what's the big takeaway from all of this? It's this. The quantum era isn't on its way. It's already here. This quiet revolution, it's happening right now. We've moved beyond the what if and into the what now. And because of that, the question is totally shifted. It's no longer if this is going to happen. It's how fast.